All right, welcome everyone to this week's Autonomy Talks. This week is a pleasure to have with us Dr. Stephen James, who is the head of robot learning at Dyson, and he's leading the Dyson Robot Learning Lab, and he's now based in London. Something about Stephen. So he completed his master's and PhD at Imperial College London, in particular working with Andrew Davison. He then moved to US, to UC Berkeley, and he was there a postdoctoral fellow with Peter Abil. And his research interests lie in developing intelligent robots that learn practical skills and behaviors in challenging environments, mostly in households. And his work has been concerned with sample-efficient reinforcement learning and imitation learning algorithms, unsupervised representation learning, and then a few shot adaptation and simulation to reality transfer. As you can see from the bio, his research has been recognized with various awards in major conferences. And today he's going to talk about sample-efficient robot learning, giving us, I think, an overview of the methods he developed with his colleagues in the past years. So I'm very excited to hear more about this topic, and therefore I give you the stage, Stephen.
Yep, thank you so much for that intro. I'm just going to dive right in. So although kind of a lot of what I'm going to talk about today is kind of within the realm of robot manipulation, it is also kind of applicable to other areas of robotics. So I figured here's the best place to start. Here's a very typical robot manipulation pipeline that some of you may be used to. Get some observations come in, RGB, depth, whatever, LiDAR. Then we'll do some scene understanding, which usually is concerned with, say, object detection, pose estimation, semantic segmentation, things like that. We build up a representation of the world, and then we can do some sort of planning in it. So we may have a set of objects that we want to interact with, and some heuristics on how we want to grasp those objects. So in this phase, we'll do some planning. Then we'll actually plan how to get there. And then finally, we'll do some sort of control loop, whether it be open or closed, to actually perform these series of actions. So this is a framework that's been used for many decades, and it has a lot of perks. They can be kind of developed independently. They have very interpretable outputs. So, you know, an output of a segmentation map is very kind of clean, and you can inspect it and get a good understanding of what's good and what's bad. And, you know, it has a proven track record that they've been used in many great applications over the years. They also have some downsides. Error propagation, for one. If you make a mistake in one of the later module, in the earlier modules, it can then propagate down to the later module. So, for example, if you estimate the pose of the cup that you're trying to grasp, then you can imagine that then obviously your grasp plan is going to be off, and then the subsequent motion planning, the motion that you execute will also be wrong. And generalizability is another issue here. So, if you design a pipeline for a particular task, you tend to find that almost the entire many modules of the pipeline have to be completely rewritten. So this may be like the control aspect. If you're going from, say, a wiping the table task to a kind of pick and place, the types of controls you're going to need there are going to be very different. And the types of planning and detection that you're going to need are going to be very different. And so you kind of, each of these individual modules normally have to be slightly tweaked. And they can also become very, very complex, especially as the tasks or the repertoire of tasks you want to do grows. It can cause the system to become very, very complex in the end. So another alternative, perhaps at the other end of the spectrum, is to do a more end-to-end approach, or a data-driven approach, where you kind of map observations that are coming in directly to some sort of action, whether it be, say, delta, end effector pose, or joint velocities, whatever. And you kind of flow the gradients through this a neural network or something like that. And there is a whole lot of issues with these setups, with this setup as well. The one that I'm going to focus on today, just because, you know, we're looking at sample efficiency, is this aspect of these methods tend to be very sample inefficient. So here's just kind of like 2 papers I pulled here, relatively recent, that, you know, we're looking at 0.2 billion samples to accomplish a set of tasks here. And also, if you look on the bottom right, there's some work here from a while ago now, that the famous farm work. And although it was incredibly impressive, I think it did show that the amount of data that you need for these approaches is quite immense. And I believe this was several months of data collection with the arms, like a set of 12 to 18 arms running continuously. So yeah, in this talk, we're going to be looking at sample efficiency within the realm of robot learning. And I'm going to kind of cover 4 main topics. We're going to look at architectural advances to help with sample efficiency, improved policy parameterizations, how we can use model-based learning or world models to help with reducing the number of samples we need in the real world, and then also how we can leverage pre-training in order to help learn downstream tasks much quicker. And all of the work that I'm going to talk about today is work I've done either by myself or with colleagues at both Imperial College London and Berkeley. So let's start with some architectural advances. So I talked about 2 kind of main categories for this kind of doing manipulation. One was the pipelines, one was the end-to-end. But I actually like this concept here, which is one where you have a bit of a fusion of both. And I kind of talk a bit about this in my thesis. I call it tightly coupled manipulation pipelines. And the idea here is that, you still have some sort of structure and you can have modules in between. These modules can be pretty much whatever you like. But the main thing here is that they all share some sort of task reward, some notion of, did I complete the task or not? And so you're not necessarily flowing gradients through these modules as you would perhaps in a more end-to-end approach, but instead you're sharing kind of a task reward. And so you can imagine here, this first box could be something akin to some sort of like pose estimation system that's not necessarily trained in a supervised manner to output pose, but is trained directly on whether it was able to successfully pick up the cup in the end or not. And a kind of series of work that follows this way of thinking is the Q attention line of work. And I'm going to talk about that now. So the very kind of first work in this line of work was Q attention with ARM, and ARM being attention-driven robotic manipulation. So this is a kind of system that encompasses 3 core agents. There's a Q attention agent, a next best pose agent, and then a control agent. So the Q attention agent, its job is to take in RGB and point cloud information. And then essentially it's an agent that's trained to choose the most interesting point in the image. So you can think of it as kind of the reinforcement learning environment is like the image itself, where the pixels are actions. And so the agent then learns to kind of focus on things that eventually lead to task success. And so you have one agent performing some interesting pixel locations. You can then crop these areas and feed these into another agent. This is the next best pose agent. And this agent's job is to essentially output where in 3D space is the next interesting place to go to. So it's meant to take these crops, and you can see here that it's highlighted the saucepan lid. And so it may output the next best pose to be slightly above that saucepan lid. And then finally, there's the control agent, which you see on the far right, which takes in this next best pose and outputs a series of velocity commands. And so in our setup, in this original piece of work, this control agent was just a motion planner. But in theory, it could really be anything. Perhaps a goal-conditioned reinforcement learning agent or behavior cloning agent. But the kind of key idea here is you have 3 sets of agents, and they're all trained with, except for the motion planning agent, they're all trained with the same task reward. And so we evaluate this setup on RL Bench, which is a benchmark full of about 100 tasks, varying difficulty. And the main kind of focus of the benchmark is on vision-based tasks, as well as sparse rewards. And so because it's sparse reward-based, exploration is very, very challenging. you have to pretty much accidentally succeed at the task, which is pretty much impossible for all RO bench tasks. And so what we do is we actually initialize the policies with 100 demos in this case. And then it takes these 100 demos and then gets to explore after kind of analyzing those demos. And you can see here that our approach when compared against kind of other state-of-the-art methods at the time, is able to significantly outperform. So, and this is was the reality back when we started doing this work, that is if you take all of these very, very common reinforcement learning algorithms off the shelf and you try and run them, they just don't perform very well on these very kind of complex vision-based tasks with sparse rewards. So yeah, that was the first work to look at the kind of Q attention framework. And then we extended it to something quite different in the end. But the main benefit it gave us was the ability to run things in the real world. So in a nutshell, really, coarse-to-fine Q attention is a replacement for the Q attention agent and the next best pose agent within ARM, which is the original framework I just talked about. You can think of it as a architectural hierarchy that allows discretization of a large continuous translation space. So let's just kind of walk through it step by step. You have a bunch of camera inputs coming in. It could be just be one camera if you're using it, but the nice setup here is that we can use any number, and we voxelize all this information into a very kind of coarse voxel grid, something like maybe 32 cubed, but that could also be smaller. And then so just like we did before with the Q attention, choosing pixels, this time it's choosing in 3D space. So it's choosing the kind of the next best voxel to look at, like where in this course scene is most interesting I should be looking at, and where do I want to find out some maybe more 3D information. Because of course this is a neural network and there's only so much data that we can pass in. We're kind of a GPU memory bounded, right? So we have to, we would ideally want to pass in these very, very large voxel grids of the entire scene at a kind of very high resolution, but we can't do that because of memory limits. So instead, this is a solution to that, where we start at a very coarse level, we choose the most interesting voxel, and then what we can do is essentially, you can think of it as zooming in. So we choose where the agent thought was most interesting, zooming to that point and re-voxelize. But now we kind of constrain the bounds such that we get a much higher resolution this time. And so you can see many more features, right? You can start to make out that there's a soft spin in the scene. And you can basically iteratively apply this. So you can have up to n of these kind of stacked, going from coarse to fine. And ultimately, what you end up with actually is a continuous output. If you keep going, the resolution gets so fine such that you end up with a kind of near continuous translation output, and you haven't had to use a kind of continuous reinforcement learning algorithm. You've instead just used a discrete one. And so, yeah, we get our translation out, and then we can maybe use the final Q attention level to also predict, say, the rotation and gripper action. And so now we have our next best pose come out. And we can give this, as before in the previous ARM setup, to a control agent, which again could be a motion planner, and indeed is a motion planner in our setup, but could really be anything. And as before, the entire stack is trained with, or they all share the same reward, but there's no gradients passing. So this is the important distinction here. So if the top agent chooses a very bad, say, area to zoom into, then obviously the lower down agents aren't going to have the information to get to give meaningful actions. It'll literally be impossible for them to do that. And so they'll get a bad reward, but so also will the top agent. And so eventually you can really think of this as a kind of multi-agent system that kind of eventually converges to equilibrium. And here's just an example of what this looks like in RL bench. So if you look on the left here, this is the kind of full scene view. Top right is the Q attention depth at depth 0. So you can see it's quite coarse. And then here's the Q attention at depth 1, which is a bit more fine. And the flashing red voxel is where the agent finds most interesting. And then here's another example with putting trash in bin. And as before, we compare this in RL bench and compare with the kind of previous baselines that I already showed before, but also ARM. And as you can see, it's significantly more sample efficient even than ARM. And this is really great because we're now at a point where we can start to use this in the real world. Another important thing to note here actually is that everything bar the blue curve, which is coarse-to-fine ARM, is using 100 demos. Coarse-to-fine ARM is using 10 demos. So it's able to actually get a higher performance more quickly with using less demonstrations. And then another side effect of using coarse-to-fine ARM over ARM is that actually by out of the box, it's able to support multiple cameras because you're just kind of voxelizing to this kind of canonical space. Whereas in the original ARM setup, you couldn't do that. You had to have, say, multiple initialized heads to feed in each camera space. But without any architectural changes, you're able to instantly use multiple cameras. And so here we show how performance can vary just by adding in more cameras into the scene across a range of different tasks here. So in red, we have one camera, the performance of using just one camera as input, and then the performance of using 3 cameras. And as I mentioned, we're now at the point where we can actually run this reinforcement learning algorithm in the real world and train it directly from scratch. So what you're going to watch here is, to the best that I think me and my colleagues know, is the first kind of vision-based reinforcement learning approach trained in the real world from scratch to accomplish, quite a sophisticated task in terms of what's in the literature today in terms of RL standards. In about 6 to, I think, 7 minutes ish. So it takes in these 3 demonstrations. And this is simply because, as I said before, the agent needs some notion of like what it's meant to do. It's completely randomly initialized. And so you could, in theory, run it without rewards for a task like this, but it could take perhaps several days to actually figure out what's going on. So what you saw in that previous clip was me giving some demonstrations, and now I'm observing it as it uses those demonstrations as well as some exploring time to try and accomplish a task in different configurations. So you just saw that about 3 minutes go by, and this is because it's all in real time. There's no kind of cutting here. While it was just sitting there, it was actually training on the data. So it already had those demonstration data, as well as that kind of one try exploration rollout that it did. And then it was just training while it was just waiting there. And so, yeah, you can see after around about, five-ish minutes, it's pretty much mastered this task. Okay. So following that, we kind of had 2 follow-up works to kind of improve on some of the weaknesses that we didn't like in coarse-to-fine Q attention. So the first one was this tree expansion extension. And the best way to kind of motivate what's going on here is with an example. So imagine we had these 3 cubes, and they have the numbers 1, 2, and 3. If you're in the coarse-to-fine setup, obviously at the very coarse level, it's very difficult to see what the numbers are on the cubes because of the coarse voxelization. And you can see an example of that here. So we kind of call this phenomenon coarse ambiguity. And it's very hard in, say, the setup checkers case to see what the state of the board is in this depth 0, as well as pick and lift small. Each of these shapes, so each of these kind of blue shapes here are different. And so if I ask the robot to pick up a very particular shape, for example, the moon shape, it has no idea really at depth 0. So it's pretty much a coin toss which area it should zoom into. And so what we wanted to do then is give the Q attention a way to, instead of just looking at one, kind of zooming down at one point into the scene, have the ability to choose multiple different areas at the coarse level, essentially do a beam search to expand all those areas, and then accumulate values from the coarsest levels back up, the finest levels back up to the coarse level. And so what that means is essentially that the coarse level then gets a much better idea of the value that the finer levels are saying. And so it's able to make much more informed decisions about what high level action to take. And so we evaluate this on tasks that we know coarse-to-fine arm would do particularly bad on. And so things like setup checkers is a great example because the state of the board is so hard to read. Pick and lift small, again, if you it's tasked to pick up the block with the number 1 on it, but it can't be read. And so, oh wait, sorry, that's lift number block. Pick and lift small is to pick up a particular shape, but all the shapes on the table are the same color. And so you can see here, there's quite a big difference between using this tree expansion method, which is in red, versus the original coarse-to-fine arm setup. And then we also ran this in the real world too, where the task was to reach this shape here as the target among 2 distractors. And if you see on the left here, this is what the observations are to the robot. So at a very, very coarse level, it's going to be very hard for the agent to see what's going on. So what we do here is, as before, we kind of train it with some, we give some demonstrations. Again, 3, I believe, in this case. And then we train it. And now what we're about to show here is how coarse-to-fine did at test time and how the new tree expansion did at test time. And so you can pretty much see that, coarse-to-fine arm is essentially is a coin toss between which one it's going to reach for. Okay, and then finally, there is the learn path ranking extension. So this is a kind of very high level view of what coarse-to-fine arm is. It composes of the coarse-to-fine Q attention, which gives you the next best pose. You give it to a path planner, you get a path out, and you execute that path. So this green is the learned section, and this kind of yellow beige is non-learned because it's a path planner. So the issue here is that if we have a task like this, so you can see that if we wanted to lift the toilet seat, there are multiple different paths that you can go to get to the endpoint. So this could be like the next best pose, but actually only a very few of them, or a subset of them, are the correct path you actually want to do, because all the other ones are invalid and you'll end up breaking something or the arm. And so in the current setup, coarse-to-fine arm can't do this, right? Because it's just using a motion planning. There's no concept of constraints here, right? Because we don't know, the whole idea here is that we don't know what our task is going to be. It's entirely data-driven. So we can't just impose that the planner has some sort of joint constraint or something like that, because then we're imposing human knowledge into the algorithm, which is not what we want to do. And so what we do is instead of just having a planner that kind of maybe outputs multiple paths and then trims them down just by length, we instead actually generate a load of different plans using, say, a traditional path planner. And then also we can get other ways of generating paths. For example, you could just generate a bunch of, say, Bezier curves. And so on. You could have other things going on here, but the idea is you just get a bunch of different ways of getting your paths out, and then you learn a trajectory ranking Q function. And that basically learns to rank based, again, on fully on task reward, which path is likely is the highest value, which one is likely to lead to success of the task. And so as training goes on, and we roll out in the environment as the agent's exploring and maybe successfully achieving a task, we're actually getting trajectories out that we know successfully did the task because it got rewarded. And so what we can do is keep those trajectories in like a separate data set and actually in the loop start also performing a path policy. So, this could be a reinforcement learning agent, right? But in our case, we use it as a behavioral learning agent and train all of the we use all of the paths that are previously known to be correct to then train this in a supervised learning manner. And so what eventually happens over time is that because the path policy is a distillation of all the previously good paths we've taken, ideally towards the end of training, this path policy should be pretty much always outputting the path that is chosen by the trajectory ranker. And so essentially you can then throw away these other two sampling-based methods and get a much kind of quicker turnaround time for your policy execution. And so what's nice about this is that at the very beginning, your path policy is not going to be very good. And so we have these kind of backup path planners and the Bezier curve generator. And so that's great because we can kind of continue to do sensible things. We know how to do motion planning pretty well, and it works, in a lot of scenarios. So let's use that. So that's the concept here. And then, but it also kind of acknowledge that actually, if we want to be fully data driven, and we don't necessarily know what the test time constraints are going to be, then somehow distilling this knowledge into an actual generative model is perhaps the best way to go forward. And yeah, we run these on a bunch of experiments in RL Bench, and these are all tasks that have some sort of notion of, there's only a few correct paths to actually accomplish tasks. And these are mostly tasks, which are on articulated objects, because those are the ones that, there's only a few motions that you can do to actually say, open a box, open a door, and a bunch of other paths you're going to do aren't going to lead to task success. Okay. So how are we doing for time? Okay, I'm actually going to skip over policy parameterization and we'll go straight to model-based RL. Okay, so with model-based RL, we have this pretty standard setup, right? Where we've got, with model-free RL, we have this setup where we have an agent interacting with an environment, and the environment gives you some state and reward, and the agent is given some actions out. And in a model-free setup, we're actively kind of using that data to kind of update our agent as it's exploring in the world. So we're directly training on that data that we're getting as we explore. In a model-based setup, it's a little bit different, and there's multiple different ways you can use model-based RL. But here's one particular way where you have a policy that's interacting with an environment. It gets some observations out. And you, instead of training on that data, having your agent train on that data and learn from it, you instead learn a world model in a self-supervised fashion. So a model that takes in the observation and predicts, say, an action, and then predicts the next state and reward that you get. And then what you can do is have the policy actually train in that world model. So it doesn't necessarily even have to train in the real world anymore, because all of the real world data is being used to train your world model. And you can just directly train the agent in that world model, because it should ideally, with enough data, reflect the true real world. And so a question here is, well, how do we learn some good representations, visual representations for the world model? That's a really important part of the model, is to predict the next state. And so a good way of learning representations that's come out of the vision community is MAE, masked autoencoders, which is essentially the kind of main novelty, I guess, is taking a VIT and showing that if you do very, very high masking ratios, and you essentially do image reconstruction, you get very, very good representations that are learned. And so what we wanted to look at is how to use these MAE models inside of learning a world model. And so if we look at how you can actually train a world model, you can kind of train it all together as one big setup. So you're taking in OFT, you're you're feeding this into some sort of maybe encoder decoder setup, and reconstructing from Z of T, and then also reconstructing the reward that you get, as well as the next state that you end up with. The issue with doing this all in one is that there's a trade-off between the kind of visual reconstruction, so the kind of image representations that you're learning, but also the dynamic representations, and one of them may have to give. And so that may not be the best way of doing this. Another way that you could do this perhaps then is to instead train the encoder decoder first. So you just learn the visual representations first, and then you train the dynamics model on top of the, say, VAE features. But then this may also not be good, because your features that you learned during the image reconstruction may not be kind of relevant for the dynamics learning task, as they may not kind of capture the kind of task relevant things that are going on. So what we looked at is trying to kind of deal with these, improve upon these issues in learning world models, as well as trying to include the benefits that the vision community has seen from using MAE. And we do this by kind of splitting our approach into two setups. So we have the visual representation learning phase that takes in an observation, does MAE, and I'll talk about mask-com features in just a second, and then also predicts this reward auxiliary output. And that kind of helps this encoder decoder setup, the visual representation learning side of things, to also kind of focus on task relevant things, because if it doesn't, then it won't be able to predict the reward. And then we also then train the dynamics prediction task. We alternate between the dynamics learning side of things and the visual representation learning side of things. So we'll do a few steps of visual representation learning, followed by a few steps of learning the dynamics. And so you may be wondering why we have these mask-com features here. And the reason being is that if we just kind of simply apply MAE to manipulation task, we actually don't get very good image reconstructions, and thus don't get good representations. And the reason being is that in the vision community, obviously you've got natural images where there's a lot of structure. Normally the thing that you're trying to reconstruct is like a large image, for example, a dog that's in frame. Whereas in, say, robotics tasks, we may have a lot of small objects on the table. And if, as you can see, when you apply large masking, you actually lose a lot of the details of the objects. And so the representations you may learn tend not to be very good. And so what we apply is this mask conv, instead of masking the actual pixels themselves, we actually first send the image to a set of convolutions and then mask those convolution features instead. And that means that there's a little bit of kind of local sharing of information before you actually do the masking. And so you're able to learn much better representations then, especially on setups where there's small objects. And so when we apply this to a set of tasks in both MetaWorld and RL Bench, we're able to outperform a method that we're building on top of, which is this Dreamer v2, which is another kind of model-based RL setup. Okay. So now we'll move on to the final topic, which is pre-training for robotics. And so why I think this is important is because we've talked about like algorithmic choices to improving sample efficiency, but there's also the concept of like, okay, how can we leverage a bunch of data that already exists out there in order to learn very, very rich representations. So we basically can use the same methods, but it's more of a kind of data iteration that we're doing here. And so what we looked at is how can we use videos from, say, or natural videos, for example, this Epic Kitchens data set, to learn an action-free video prediction model. So remember, because we're just observing real world, we actually don't have action labels, so it has to be action-free. And then once we kind of learn this action-free video prediction model, we can use those representations that I've learned, combine it with a action condition world model, and then we get the benefit of using we get the benefit of the in the wild data, while also then making it applicable for kind of downstream controlled tasks. And so here's just a bit more details here. So we can have something like this latent video prediction model, which takes in some frames, and then you do video prediction in a latent space, and then you can say at a later Z reconstruct later frames, so not having to do this in a, say, autoaggressive fashion. And so we would say pre-train on, say, RL Bench is a good example here, but we don't have actions. We just have a large data set of the robots doing interesting things. And what we can then do is take the representations that we learned, which is these the encoders down here, and then slap on a world model setups where we take in the video prediction latents and then predict the state, the next state and reward from the action. And so we're basically leveraging the representations that we learned during the pre-train phase when we didn't have actions, and then we can use those in addition to adding on a few extra MLP layers to then adapt those representations to be used in an action condition setting. And then we have a very, very similar setup actually to what we previously had, where we have the agents training within this world model, and we're able to get much better sample efficiency. And so we compare to, again, Dreamer, because it's a very similar setup that we were building upon. And we're able to show that by leveraging data from another domain, which in this case, and these plots, I believe, was RL Bench. So we were training the action-free training was done in RL Bench. We just had a huge collection of images without actions of the robot doing things. And then we actually fine-tuned in MetaWorld on several tasks and show that we're able to outperform Dreamer when it's also kind of put in a similar setup. Okay, and finally, we have the setup of what if you have a bunch of tasks, a set of training tasks, and you have an infinite amount of time budget to be able to do something with those tasks. for example, say learn representations with them. And then you're in the test time setup, you have a finite amount of time budget that you want to be able to kind of quickly learn new tasks. And so it's a little bit different than the setup I talked to before, in the sense that you're using, say, in the wild unsupervised data. Whereas here we're saying, okay, well, let's say we do have supervised data. Let's say we do have a bunch of tasks and we have like a way of giving rewards. How can we then leverage that information such that then you can learn new tasks later down the line much quicker? And kind of how I like to think about this is how you perhaps, when you go to school when you're a kid, like you are learning all these sorts of different things, and you're learning all sorts of tasks and all sorts of subjects. But then when you leave school, the idea is that, you're going to be learning new things, but you should be able to leverage the knowledge that you learned in school to be able to quickly learn new tasks. And so when I talk about this, maybe two kind of similar areas might come to mind. One is multitask learning, where the idea is you have a bunch of tasks that you want to learn. And then the goal is to essentially be able to perform all those tasks at the end. So you have a single agent or a single model that can perform all tasks. And then you have another setup, which is meta learning, where you're essentially learning to learn. So you have all these tasks, and the goal isn't necessarily to be good at those tasks, but it's actually instead to have a way such that at test time, you can quickly learn new tasks. So there's a kind of subtle difference here between these two. So what I just talked about on the previous slide, which one sounds more ideal? Well, meta learning is the one that sounds like what we want to do, right? We have a bunch of tasks, and then at test time, we want to quickly learn ones as quickly as possible. But we actually, if you look at the meta learning community within kind of the robotics domain, you'll notice that actually what they do is tends not to be different tasks, but different variations of the same task. So, for example, it might be one task is to push the banana to the apple, and then a different task might be to push the banana to a pear or something like that, and that is classified as a different task. Well, obviously, in reality, that's not really what we want. We want different tasks to mean entirely different things. For example, pushing an object versus a pick and place task, for example. And so we noticed that there's a lot of there's a big gap in the meta learning community. And another thing we noticed actually is that nobody was doing the or at least I should say, there was no direct comparison between, say, the meta learning paradigm and this multitask pre-training paradigm, where instead of multitask learning, where you try and learn all the tasks and then be able to perform all those tasks, you instead learn all the tasks in a hope that you learn good representations, such that then you just fine-tune them to then quickly learn new tasks. So you're not necessarily learning to learn during training time, you're just trying to learn to do all of them, but hope that the representations that you learn are good. And we actually found that when you apply this simple approach of training a multitask setup and then fine-tuning them, that they get the same as or better than all existing meta learning approaches that we tried. And I think this was a really important lesson, because it shows what can happen if two communities perhaps don't communicate, or the right baselines aren't used. Then it's very, very hard to see what is the best way to do this sort of problem. And so this was a really great result, because actually fine-tuning simple multitask pre-training and fine-tuning those, which is the one in orange here, is actually significantly cheaper to run as well. For example, Reptile is quite expensive, as it actually each gradient step is actually multiple mini gradient steps that have to be done. And so it's actually quite an expensive learning pipeline to run. And actually kind of is quite similar at the end of the day to a fine-tuning approach. It's just more complex to run, more expensive, computation expensive. And so, yeah, we run this across 3 different environments, ProcGen, RLBench, and Atari, and show kind of similar trends between the 3 environments. And I think on the kind of final note here, I think the most kind of interesting thing that came to light was when we run Coarse-to-fine ARM on a set of RLBench tasks, and we pre-trained on 10 train tasks and then fine-tuned on these test tasks. So these 5 tasks here are they're all test tasks. They haven't been seen during the pre-training setup, and they get 0 demonstrations. They're actually able to do very well and actually succeed with sparse rewards and vision-based. So I think this was quite a very welcome surprise in the end, that actually, even from a very few number of pre-training tasks, we're able to learn good enough representations that we're able to accomplish quite complex tasks at test time. And then we also kind of abalate on a series of other sets of demos as well. So same tasks, but varying numbers of demos, and show how the performance changes over time. Okay, and I think that is perfect timing. All the papers here I talked about today are here. And yeah, all of these were done during time at Berkeley and Imperial. And then at the bottom here, we have some videos from Coarse-to-fine. Thanks.
Thank you, Stephen, for the great talk. Let's open now the stage for questions. If you have questions, you can either raise your hand and I will call you, or you can type your question in the chat and I will read it for you. So let's see. We have questions. Nobody raising hand. Nobody wants to break the ice. Actually, maybe something. Okay, I'll break the ice. Something for you to advertise a bit. Maybe Dyson, or what you are gonna do now. So what are the plans for your lab now? What are the main focuses?
Yeah. So we're interested in looking at the next generation of kind of household robotics is the goal, and we're going to continue to kind of look at how these data-driven approaches can help in that area mainly. Yeah.
Okay. So we have a question, but in the meantime, in the chat, Alberto San Miguel asks, how important is to consider control strategies when doing reinforcement learning for robots? Maybe it's a broad question, but I'll let you.
Sorry, what was the first part of that question?
So how important is to consider the control strategies when doing reinforcement learning for robots?
Control strategies, is that what you said?
Yes. Yes.
So by control strategies, I'm not sure if you mean, say, like action modes. You mean at what level of abstraction the agent is operating at?
Yeah, let's see, Alberto, maybe we'll complete the questions on the chat. See.
I mean, if I'll assume that's what Alberto meant. If it is indeed, how important is it to consider, what level of abstraction the agent is operating at? It's very important. I mean, that was the biggest lesson, I guess, from the Q attention line of work, is that, once you start getting a hierarchy of agents where each agent is maybe operating at a slightly different action mode, you end up with much better. You end up with a much better, more sample efficient approach, and that's kind of follows a lot of what's been going on in the reinforcement learning community as well. I mean, you look at all the biggest successes that RL has had, and they're all very high level actions, right? High level action domains, StarCraft, Go, all those setups. They're not operating at like velocity control, right? We're not controlling the velocity of the human hand to like move mouse clicks, right? We're operating at high level actions. And this is very similar to what we're seeing here, that if we use RL for, say, choosing the next best pose, which is a very high level action, we end up with very good sample efficiencies. And then, leaving then the control to things that we already know how to do really, really well, right? So yeah.
Right, thank you. So there is Nuria who has a question. Go ahead.
Yes, hi. So you showed two approaches, first about model-free and then after with model-based. And there's a bit of, in the community, there's a bit of discussion what's the most promising. Do you have any insights on what to focus more on, model-free or model-based?
Yeah, I would say there's that gap every day is becoming a bit more blurry now. Like, I think, I mean, the model-based approaches that I presented today are kind of a mishmash of both model-based and model-free. So, generally when you spoke of model-based approaches a few years ago, you would normally say that, you have a model or you learn a model and then you plan using that model. But what's going on here is that you're learning a model and then you're doing model-free learning, but on the model, if that makes sense. So it's a little bit different. You're not using the model necessarily for planning, you're using it as a kind of proxy environment to get more data. And it makes a lot of sense because you're using your data twice, right? You're getting more out of your data. You're using it to say update the policy, but then you can also use it as to update your model. And then, especially if you've got limited amount of samples that you can, or a limited budget to run in the real world, learning a model does become very, very important at that point. So yeah, I think that they are kind of two tools that you can use, and ultimately the best approach is going to be some sort of hybrid of the two.
Okay, thanks.
I'd also point out that the model-free stuff that I covered at the beginning with coarse-to-fine queue attention could just be combined with a model-based setup as well, and I'm sure you might be able to get even better sample efficiency improvements.
Nice questions. So next question is from Carlo. Go ahead.
Hi, Stephen. Thank you for the great talk. It was really impressive.
Hi, thanks.
My question is more on the last part, the comparison you made between meta learning and fine tuning. I found it very insightful, but my question is more, in addition to the findings, where do you think is the issue with meta learning? Why have people just focused on variation of tasks rather than completely different tasks?
Yeah. Why? I guess it's hard, right? I mean, we couldn't get it to work very well. I mean, if I go back to these graphs, maybe you'll see that, Pearl, I mean, on a lot of these, only Reptile seems to do pretty well, and that's mostly because it actually ends up being, when you boil it down to one inner gradient step, it essentially equates to a simple kind of pre-training setup. And yeah, that's why I don't think people have been doing it, because the problem setup was just very different, right? The benchmarks that existed weren't really challenging them. Whereas in the vision community, the benchmarks were much more difficult. From the get-go, if you look at meta learning a few years ago in the vision community, different tasks were, classifying dogs from plants. Those are completely different tasks. They weren't trying to classify German Shepherds versus Labradors or something, and that be the different task, which is essentially where we were in the meta RL community. So what we were trying to do with this paper is just like, A, don't forget to use like a really simple baseline, which is this multitask pre-training setup, and B, we should really be using harder based benchmarks. And of course, now there is RL Bench, there is Meta World, and so there's two benchmarks out there. It seems that the focus on the community is still on kind of trying to solve individual tasks as well, with less of an emphasis on trying to use them for meta RL.
Thanks.
Nice. All right. Any other, or maybe any closing questions? Didn't see other raise hands. There's people saying thanks for the talk. Okay, there is maybe a last question. Hi, Mr. James. Thank you for the presentation. I would like to ask, what kind of computers do you use for learning models? For example, do you use like HPCs or just working on local workstations on your office? Maybe that's more of a logistical question.
Yes, yeah, a bit of both. Mostly we use like local servers to do training, but yeah, for initial testing, we'll use desktops.
All right. And with this, I think I want to thank you again, Stephen. Great talk, and good luck for the start of your lab.
Yeah, thank you so much. Thanks everyone for joining.
Great.
Bye.
And see you all next week for the next Autonomy Talk. Bye.